continue right now, but did they use the SOS or SOT?
You use sub S.
SOS. Right, so continue with the proof of magnitude. Continue. And probability and S K is probability that I have T K what is less than S. T K plus a little tau K equals 1 greater than S. Correct here, and then I'm going to invoke the fact that the big T and the little tau are independent. So the Tk run from 0 to S. So this could be thought as B of Tk, right? F of Tk. Well, I guess let me call this to be my x here at Tkx. Integral from what? So the little tau running from S minus x up to infinity dy, and then f of tau can plus 1. This is because the domain that I'm looking at is what is it? Tk running to S and tau k running here. This is my domain of integration. This is S minus x. This is my y. So this is S minus x. Okay. So I have to plug in. So tau is exponential, and this is 0 to S. F of the big Tk little x, and this is right here is what? This is e to the minus lambda S minus x. So okay, e minus lambda S minus x dx, right? This is because this is simply the temporality of this exponential. Recall tau k exponential lambda, then the CDF f of t is 1 minus e minus delta t, and the tail probability of tau k greater than little t is e minus delta t. Recall this is the integral from t to infinity of the density lambda e minus delta d. Alright. And then just have to plug in here. So now this Tk, the capital Tk is the sum of the little tau, and that is a gamma. So 0 S, what do I have here? So I have density for gamma distribution, so lambda k over gamma k x to the, I believe, minus, sorry, e to the minus x, right? This is because the Tk is a gamma distribution, so maybe just write it up. So we call Tk being the summation of little tau I of k. This is a gamma distribution with the alpha, beta, and beta number. And the density is just given by, again, this is lambda to the, lambda, sorry, this is k. So lambda to the k, x, k minus 1, e minus lambda x over gamma k. Alright. So, then have a quantity from the middle tau, so e minus lambda s minus x. Yes. Am I missing anything? I am missing the power. Alright. Yeah. I mean, I just substituted the density of the gamma. Very simple. Now I'm sure up to this point it's actually not difficult because you now pull out the constant. So actually the constant is lambda to the k, e minus lambda s over gamma k, and I am left inside of this 0 to s, x k minus 1 dx. Because the quantity exponential of minus lambda x is gone. So this quantity here is cancelled out. So that integral is pretty straightforward. That's that integral is clear. Pretty easy here. That is simply s to the k over k. So combining everything, lambda k, e minus lambda s, s to the k, gamma k here is k minus 1 factorial. So you have k minus 1 factorial. Multiply with k, and combining everything is main. Well, I guess I want to write in terms of the Poisson mass function e minus lambda s, and lambda s to the k over k factorial. This is the mass function, the pure math of a Poisson with parameter lambdas. Okay, let me move on to the next terminology. I'm gonna denote by notation given a fixed time s, a fixed time s. I'm gonna denote by tau 1 is the difference. So I have, this is my time rest. T of the time of the NS arrival, and this is T NS first one, and we're going to call this difference to be tau 1 point. So that will be equal to t of ns plus 1 minus this. This could be thought as the first arrival time. First arrival time after so I guess this is not really the first arrival time. It should be the waiting time for the first arrival. I would say waiting time after s. Seems I guess waiting time since time s for the first arrival. Does that make sense? This is the amount of time I have to wait for the first arrival after time s. I guess is the wording kind of confusing, or is that clear with the wording? Waiting time for the first arrival after time s. Right. Similarly, I'm going to define tau k prime now is simply what do I have here? So t and s plus that will be ns plus k minus t and s plus k minus 1. So this could be thought as, so again, I have t sub ns. This is time s here. T and s plus 1. This is t sub ns plus k minus 1. This is the ns plus k. So this difference is tau prime k. Yes, please.
Will that be the tau k prime is equal to the t nx plus k subtract the s?
This is not tau k. This is not really a tau k. You have to condition on this random variable in order to get back the tau.
Oh, okay, so just the tau 1 prime is you already have the time as for the tau k. You only compare the tau k to kind of the nx plus k subtract 1. Just one term.
Comparable.
Just compare the.
I mean, yes. So heuristically, this is the same as the tau above there. Heuristically. But the thing is, this is random depending on the ns here. And so suppose you fixed. Suppose you have a given ns be it say say be it a fixed number. Let's say number a, for instance. Then this is the same as, then suppose you fix this. I guess let me write down rigorously to avoid confusion. So okay, so I guess put the remark here maybe. Remark. Given ns be in a little m, say, all right, then tau prime k, given this information is basically the same as what? So if this is n, then I have that will be tau, little tau of, I believe that is tau m plus k. Of course, I need to condition on this. This could be thought as I have so given this information, that means this is Tn and that's Tn. So that's here Tn plus 1. So this this is tau, this is little tau k. Am I correct? No, it should be tau m plus k. Right? And this is the same thing as the tau prime m plus k, which is tau prime. Where is that? Tau prime with k. I guess I'm going to say tau prime k. So, tau prime k. Yeah? Does that make sense? So if I tell you the exactly the number of the arrival before time s, suppose it gives you that information, then the tau prime is the same as the tau. Basically. I mean, you should say it has the same distribution. I should say it has the same distribution. But in general, they not really the same. Generally. I would say they're not the same, even though you will see that they will, in fact, they will have the same distribution as an exponential. I guess I want to say, well, I guess I want to say this. I guess this is what we, I mean, they should be the same now. But in any case, so, I mean, why would I introduce this kind of tau prime here? That to prepare for the big theorem that will hopefully be able to mention at the end of class. For now, let me give the property of this tau prime here. This tau prime, so tau prime little k here, they are IRE distributed as exponential lambda. Okay. And we'll say mutually independent of s. Alright. So that means, suppose I have that number ns arrival before time s, then whatever happens in the future is independent of the past. Okay? So the future is independent of the whatever happens before time s. Okay. So, proof here. So step one, I want to show tau k prime is exponential lambda. So there, as you can see from this definition, this is tau prime here starting from the count starting from the last. And this for any k starting from 2, this is for k, starting from 2, pretty much similarly to the little tau, so that I will have to split. So now if k being, so now let's just considering the easiest case, suppose k starting from 2, then what do I have? I have the probability I want to evaluate this event. Right. I want to evaluate this event could get to this formula, then that is enough to say tau k prime has an exponential. So you need to show, well, basically you need to show this probability is E minus lambda. That's what I need to show. And now I'm going to show this, or we just, well, condition on the number of the arrivals before time. So this is equal to summation on, let's say I'm running on little I from 0 up to infinity, probability tau k prime greater than t, and s, b, and I. Okay. Or maybe, well, I guess I want to stick with that remark here for the notation. So this is n, and that's b. So that is better. Okay. And then, now suppose if I know I have n number of guests before time s, then the tau k prime is simply this tau n plus k, right? So this is the same as n in 0, infinity, probability of tau n plus k greater than t, and of s. Okay. And then we're invoke the fact that the ns, b and n, that is the same as, so these guys here, they are independent of whatever happens right here. So I guess it should be a little bit more, well, I'll just rewrite this, infinity n plus k greater than t. This is the same as I have t n is less than s, t n plus tau n plus 1 is greater than s. Right? And now you know that because k is at least 2, and so this event here and this event, they are independent. Because this event depends on this little tau n plus k. This only depends up to tau n plus 1. So technically, this is what? This is the same as, well, I guess I'm going to write this, right? Little tau, tau I from 1 to m. And this is basically tau I from 1 to m plus 1. Right? So only depends on all the tau I up to m plus 1 index. This depends on a tau n plus k, where k is starting from 2, so they're independent. So you can split them up. Because tau n plus k independent of the collection tau 1 up to tau n plus 1. Since k is at least 2. And so I am easily splitting this up as tau n plus k greater than t multiplied with the other guy, but that is the same as ns b and n. This is n starting from 0 up to infinity, and this is e minus lambda t. this is one. Which is E minus L. Right. Is the function? Yes, so in order to specify this, yes, let me just sketch it out here. So it's easy to see here. Yes. So this is T1, this is little tau 1, T2, little tau 2, and this is tau A, and this is tau A plus 1, here minus here. I hope the graph is clear for the sake of the independent argument over there. Right. So now that is for the k being at least 2, so now if k is exactly 1. Right, so now because the tau 1 prime according to that definition, right? So as usual, I have probability tau 1 prime greater than t, the same as the probability of tau 1 prime. Well, I guess I want to look in maybe tau 1 prime is greater than t here, and the usual n is being n starting from 0. Alright. So now if and this is exactly n, then plug it in. That is the same as summation probability of tau 1. Sorry, this will be like tau n plus 1. That is, well, so I guess I want to say, right, so this is tau n plus 1 minus so s minus t n greater than t, and that's t. You go back at this, but so you look at this here. This distance here is my tau 1 prime. Right. This little distance is my tau 1 prime. Given that I have n guests before time s. So this is equal to tau n plus 1 minus this distance. So this is equal to tau n plus 1 minus the ln s minus t. Yeah? So I'll keep that graph just to help. So over here. And this is the same as summation of n. Probability tau n plus 1 greater than now t plus s minus t n. Now I'm gonna rewrite the NSP name. That means s minus, so that means tn less than s plus tn plus tau n plus 1 is greater than s. could be rewritten again as this is like tau n plus 1 is greater than s minus tn, and s minus tn is positive. Alright. And now we'll so what to do next now? Up to this point, I will invoke the so-called memoryless property. The so-called memoryless property is heuristically, this is an exponential, right? I already bigger than that. Then the probability I am bigger than that plus another piece is the same as. This is pretty much, of course, I got a condition on this. Really, tau n plus 1 greater than t plus s minus tn. Condition on tau n plus 1 s minus tn. S minus tn is positive. Probability of the rest here, which is again in this medium. And this by memoryless property. This is same as probability tau n plus 1 is greater than t. Not so convincing, right? Exactly what I just explained last time. I'm bigger than some random variable, which is not a fixed number. So there is an exercise. An exercise here is so an exercise is to think about. Suppose I have an exponential lambda independent of a random, let's say continuous random variable z, which is always positive. Then the memoryless property says x greater than or equal to t plus the z, condition on x greater than z. This is equal to the probability of x greater than. Not difficult to prove it. Not difficult. Not difficult. So now you can think of this, right? So you can think of this exercise here, compare with the 1.5 here. So here I will think about s minus tn is a random variable z. All right. Given the fact that s minus tn is already positive, z is positive. Furthermore, obviously, z depends up to tn, right? Which is independent of the tau n plus 1. Because tn, again, tn, which is the summation of the tau, it's just the summation from tau 1 up to little tau n. So z independent of the tau n plus 1. Comparing that, get what we need. Okay. Question? Thought? Anyway, so now you just need to pull out this, because this is just a e minus lambda t. So that will be pulled out, and I'm going to sum on the little n here, starting from 0. So basically I have e minus lambda t, summation on n, probability of n has to be there. And that is obviously 1. Alright. And of course that is this here is equal to 1. Anyway, so I guess okay, so I guess it seems to be too much here from the math point of view. So let's just take it for granted. Alright, so I guess I'll leave this as an exercise for the second piece. Prove that they are independent, together independent with the past. Right? So step 2 exercise here. Step 2. Okay. Okay, anyway, suppose now we accept this. Suppose I accept this. And actually there is another big lemma. Let me put that as a lemma 4. In fact, the collection of tau K prime and the collection of, so I just want to say R, mutually independent of collection N1, so I can start saying okay, S1, and S2, and Sn, where this sequence of time here is increasing. So S1, S2. In other words, this, so you think about it, if I start from time S and moving forward, the independent of whatever happens in the past, that could be thought as some kind of like a Markov property, kind of like a Markov property. Okay. All right. So now I would. So now, as a consequence, we have the following theorem characterizing the Poisson. Okay, so this will be an exercise. So I'll leave that as an exercise. Okay. So now I'm moving on to the big theorem of the section. And suppose I have NS is a Poisson process. According to my definition, number 1 above, I guess I want to say NS is a Poisson process if and only if. If and only if. Following hold. From 1. 0, 2, and T plus S, that is NS. It is a Poisson process with a weight lambda 2 and 3, so-called independent increment. Anyway, I have suppose given a collection of increasing sequence of time. So 0 less than, okay, let me check that, S1, S2, up to Sn. Then, and so Sn minus Sn minus 1, all the way down to Ns2 minus Ns1, together with Ns1. This collection are mutually independent. Probably this is something you already seen before. Probably you have seen that. What does that say here? That says the number of the arrivals in each of these time intervals are independent. Okay. And reversely, suppose you have this. Suppose you have a sequence of collection Ns satisfying these properties, then necessarily, it has to be written as that, maximum definition. If and only if. So basically, this is something, probably something in the elementary from reading book. That's a definition, I'm sure. But for a more advanced from reading book, the other one is the one is a definition. But they are equivalent. They are equivalent. Okay. Alright, so let me just walk through maybe number 2, proof of alright, using the tau prime rule here. Okay. So what does it say? So I have note that's what we have. I have nt plus s minus ns. Well, you can think of this as the, so let me sketch it out here, alright? So this is my time s. This is my time s plus t. And over here, this is the last arrival before time s. T is of ns. Alright? And the last here, right? Up to here is the last arrival before time s plus t. So n is of s plus t. Okay. So what do we have? So now, according to my definition, this is tau 1 prime. This is tau 2 prime. Up to this is tau prime of, according to this would be n of s plus t minus ns. Right?
So just t.
Right. And so according to this, what lemma was that? Lemma number 4. Actually, lemma number 3 for the sake of concrete here. These random variables are independent of the ns here. And so you can say, so now, I guess I don't even need that because this is just the maximum of k, summation of tau from k, sorry, I from 1 to k, still less than k. Yeah. According to this graph here, the number of the guests arriving between from s to s plus t is the maximum to k. The maximum of the tau. And recalling since tau and I prime, they are I and D, exponential number as in level 3. Well, right. So basically, this is just kind of like another Poisson process here. So lambda sublime and t plus s minus ns must be a Poisson, with the rate being lambda t. This is the content of the level 2, according to the level 2. because, so part 3, this is pretty clear because this is so that which are independent of the NS. And so part 3 is pretty straightforward now. Because this is independent of the NS. So maybe part 3 for 2 terms here. So considering like an NS, sorry, NT plus S minus NS versus NS. Okay? So the claim is they are independent. This is because based on this observation, tau I prime has nothing to do with the NS. So since NT plus S minus NS, and this maximum depending on tau I prime less than T. This is K here, 1. And the collection of tau I prime independent of NS. This is lemma 3 again. Actually, just a, let's say lemma 4 even.